Good morning. Let's start the class. Sorry, a little delay because of the charging of the camera. Because we talk about aerobic respiration in the lab section. So we're going to move on to the next section of the exam 3, which is we talk about the bacterial genetics. This will be focused on profile is central dogma. And the central dogma will explain what happened for the bacterial genetics, the genetic transformation, which is DNA goes to RNA, and RNA goes to protein. So we will talk about is DNA replication and RNA transcription. And the last one will be translation. So we'll see, we try to finish this week. And next week we try to talk about lacto operant. Now we'll see how it goes. Now you know that in your genetics class, you may talk about this guy. RNA go back to DNA. This is called the reverse transcript. Just want to let you know there is a reverse transcription could happen. So by the time we also call it the RT-PCR is reverse transcript PCR. Right now we call RT-PCR is real-time PCR. Okay, so this basically is our platform. How we're going to talk about that. We need to talk a little bit about the history of the DNA. So we want to talk about this DNA stuff. So in the history back in 100 years ago, 150 years ago, there's a period of time people are getting together the information of genetics and biochemistry. So they try to understand, it's called transformation material. So what type of the material is transferring the genetic information during their communication? This starts is 1912. The very horrible pandemic by the time is Spanish flu. Spanish flu kills millions of people. It is severe than coronavirus, I can tell you, and it lasted about 10-15 years even. And the bacteria, what did it cause? We talk about Streptococcus pneumoniae. Or we call it a pneumococcal pneumonia. We just learned it, that's why we want to talk. Now, in 1928, F. Griffiths did a very important study, which is right on the slides, to try to get the information of a transformation happens. So we also call this a transformation principle. So Streptococcus pneumoniae, there is two different types. One type is smooth one. This is a pathogenic, which means it will cause animals die. They also, this is a smooth one. They also have a rough one. A rough one, which is kind of like a surrogate. There is no toxin, or we say no severe toxin. So he did a study on the mice. So how he did that? He used this smooth Streptococcus pneumoniae, okay? It's just this Streptococcus pneumoniae. And to inoculate a mice. And what happened? The mice is dead. And then the second step, he using a rough Streptococcus pneumoniae. inoculated the mice. Now what happened? The mice survived. So the next step, what he did, he using a heat injured, or we say heat treated Streptococcus pneumoniae to inject the mice. Now what happened? The mice survived. Okay, the last one, it is important. You do the smooth heat treated together with the rough one. Okay, this is the rough one. And then he injected a mice. What happened? He get a dead mice. The mice is dead. So what tells you? Something happens right here. There is transformation chemical there. So he did a lot of work. All his work is based on animals. So these are animal studies. And kills millions of mice or thousands of mice. Not millions or thousands of mice. However, he didn't get successful. Because he was killed during the German bombing in 1941 during the Second World War. 1941. He was killed in his lab. Otherwise, he will still continue to do. So, this first important experiment tells us there's a transformation chemicals there. But what it is? So we talk about the German bombing killed him in 1941. They have a Second World War. During the Second World War, and everybody is busy. But there is a three very important American scientists. Avery, McCarthy, and McLean, they did the study which is as reported like this. So what they do, they combined with a smooth and a rough Streptococcus pneumoniae, and then they get purified DNA. They already get the DNA. They already know this transformation chemical is DNA. And in order to know this is purified as DNA, they treated with this sample with DNase, with RNase, and with protease. And what happened is the transformation only happens when they use DNase. And using RNase and protease, it's so successful. The experiments which is shown in the picture. So, this is clarified that this transformation chemical is DNA. Now, every McCarthy and McLean, they are three scientists at Rockefeller Medical Center. Right now is New York, University of New York, the medical center. Okay, so in New York, in NYC, they did this very important research, make sure it is DNA. So at the same time, people are going to do other things. Need to verify. It is a transforming principal chemical is DNA. So what they do? This is back to 1952. We have another two very important scientists. did experiments, which is called Hershey-Chase experiment. Okay, this is not a candy bar, not a chocolate candy bar. That's Alfred Hershey, and this is Massa Chase. Okay, I think Alfred Hershey might still there, so he's later become a professor at the University of Oregon and continue to do the biochemistry research. So these are animal studies. F. Griffiths. Every McCarthy and McLeod did is on the tubes. This is already being improved. Because this is, we say the animals, we call it in vivo, and this is in vitro. Because we don't need to rely on animals. But how they did it? The Hershey-Chase research is relying on a very special stuff called the bacteriophage. So this is what happened for a phage. We mentioned about that. A phage looks like this. The outside, this is a protein. And the inside, they have a DNA. Or RNA. Okay, when they choose a phage, which is T2, it's a temperate phage, which means this phage is not going to kill bacteria. Most of phage are lytic phage. They're going to kill bacteria. This phage, they don't kill bacteria. They integrated their DNA into the chromosome and the genome of a bacteria and stay there. So they choose a T2 phage. Now we want to know protein and the DNA. We have to do some of the chemical label. So how they do? They use something called isotope, which means they are same chemical name, but the molecular weight is different. So for protein, what is a special? Which chemical is special? S35. And for the DNA, which chemical is special? P-phosphate. We're going to mention real quick. Okay? P32. So they label it. Once they label them, how they do is they let it be to attacking a bacteria. And what happened is, once the phage goes there, they will generate a lot of the young phage. Okay? Now we know about that bacteriophage is an obligate parasite. So they need to rely on a host. So there's a lot of the phage generated. And this bacteria is there. There is a big chunk of that. His DNA is from the phage. Okay, so what they do? He did the whole thing to mix it. Now, by the time it is still earlier, they don't have a centrifuge. We know that you can mix the chemicals and do a centrifuge, spin them down. They don't have a centrifuge. What they do is using a kitchen blender. When they're using a general kitchen blender to blend it, and what they gonna find? They find that on the top, this is most likely is virus, and at the bottom, this is bacteria. And what they find is P35 is majority of them are existing on the bacteria. So what this means? Which means the phage DNA labeled using isotope P32 clearly transferred integrated into the bacterial DNA and showed up. Because using the kitchen blender, bacterial weight is usually heavy and the virus is less. So which chemical you find it at is P32 is in the precipitation. So that means the DNA is transferred into the bacterial genome. So which is a fit. The story we talked about before without Avery, McCarty, and McLean, the transformation chemical is DNA. Okay, this is something important. Okay, so this is 1952. What happened is everybody knows the history. It is 1953. This is the day, this is the year everybody should remember. So we're going to move this part. It is a major breakthrough in the modern biochemistry and genetics area. So we want to talk about the structure. So we're talking about this is in 1953. Two very important scientists, Francisco Crick and James Watson. They got the Nobel Prize to find the DNA double helix. We're going to talk about that later on, okay? Francisco Crick, by the time, is a young scientist, just got a PhD from Indiana University. And he got somehow like a study abroad, so become a research scientist at Cambridge University in Cavendish Lab. James Watson is a physician, worked at the Royal Society of England. They have like a 12-year-old age difference, but they work together, they get along very well. So the literature showing that by the time they always meet together, talk, and thinking the whole day. They don't do really the research. This is called the theoretical biochemists by the time. They think about the structure, what it is. They get along very well, and very lucky. In around 1953, early, another very nice British scientist, Rosalind Franklin, showed her research experiment results to Crick and Watson. Everybody knows this is using X-ray crystallographer and showing them it is a double helix. Can you please don't talk about that? So the X-ray photographer showing the double helix. Rosalind Franklin, by the time, is working under another British scientist, Maurice Wilkins. He is the PD of the research group. So the Nobel Prize later on in 1962 awarded to Francisco Crick and James Watson and Maurice Wilkins. The reason is Rosalind Franklin passed away. And there is a story is that Crick and Watson find the DNA double helix structure and published the paper. They took Rosalind Franklin to have a trip of the whole world and the whole Europe. By the time, she already been suffered with ovarian cancer. So she passed away with only 38 years old. So they going through the Rosalind Franklin's research, find the double helix. But by the time, another American chemist, you know his name, Norris Porrin. Do you know Porrin exclusion policy when talk about the electron arrangement? He also did a lot of work and very closely to find out it is double helix. But why James Watson and Francisco Crick will be finally getting there? Because by the time they have a lunch with Shagraf. This is a great chemist from Columbia University. Shagraf had a lunch with him and tell him his recent finding, which is important Shagraf rules. Which means in a different chemical, you may have different ratio of A and T, a different ratio of different amount of A and T and different amount of G and C, but the ratio between A and T and G and C is always equals to 1. And this is Shagraf rules. With this one, they very certain the DNA structure is double helix. So they published a one-page manuscript in Nature. And we call that paper is the single most beautiful paper in the 21st century. And you can download it at WVU library. It is free. Only one page talk about the DNA double helix structure. And Rosalind Franklin's X-ray photographer results is on the second page. And there's a story that when they get the publication, when they find the results, they have to do celebration. Where they go? They are at England. Where they go? They didn't go to the bar. They go to the pub. They go to the Eagle pub. And they buy everybody 2 pounds of a beer. They tell them we find the very important research results, but nobody understands it, and everybody enjoy the beer there. So if you get a chance, go to Cambridge University. In the Cambridge, at I believe it's in the east of the Great Britain, of the England area. You can go to see the Eagle pub. They still have the frame there to memorize Francisco Crick and James Watson for their important research. Okay, so let's talk about DNA. What is DNA? So we talk about so many things. So we need to talk about what is DNA. And you learn about these things in different classes. We just want to explain to you something special here. So we talk about the history. In the microbiology textbook, they don't have a slide, so I just tell some story about that. That's DNA. So what is DNA? 3' deoxyribose nucleic acids. That's called DNA. So what is the DNA looks like? The DNA, if you want to draw a single one, it is a 5-carbon sugar coming from pentose phosphate pathway. They have, here is a base. And then, originally, this looks like this. Phosphates, but we call it a deoxy. This is gone. So that's 1', 2', 3', 4', 5'. That's a structure. So what is a DNA looks like? It has a base. It has a 5-carbon deoxyribose, and they have a phosphate. Only 3 major components. So you should know DNA is a very boring chemical. Although we talk about the molecular genetics all the time, this is a very boring chemical compared to protein. Protein, you have amino acids, you have peptides, you have a primary, secondary, tertiary structure, then folding, unfolding. It's a very boring chemical. Okay, so we want to talk about something. What the base is it? The base is ATGC. You know about that. Okay. So we don't talk about this way. The base encoding, purine and pyrimidine. So what is the structure of purine looks like? Purine is always like this. 6 carbon and 5 carbon combined. Pyrimidine is only 6 carbon. Okay, what is the base looks like? What is A? Adenine. So what's the adenine looks like? We did already, we drawn already adenine. NH2, NH. We go here, that's adenine. Okay, what is another purine? It's guanine. Okay, what is the guanine looks like? This 5 carbon looks very similar. 6 carbon, little bit different. So let's draw it. It's not difficult. It's the same. What's the difference? What's the difficult one is here. Then you go NH. And you have this guy here. And what else we're missing? Is that right? That's guanine. Okay. What is thymine? And the cytosine, that is purine. What is thymine looks like? Thymine is only a 1,6 carbon, so carbonyl group right here. Here NH, here NH. So you have HCH3. Is that right? That's thymine. Okay, what is cytosine looks like? We draw it again. But there's a little bit difference. The carbonyl group still here, this is the NH2. So this is N, this is the NH, this is H, that is H. Then you go here. Then what you're going to do? Is you're going to have to add one. Okay? That's cytosine. Okay. Then you have a uracil. That is replace CH3, the methyl group, with the H. That becomes a uracil. We'll talk on Thursday. Okay, so that's the ATGC, what it looks like. How they connected with each other? We talk about is A complement with T, G complement with C. So, if you want to talk about the DNA structure, what it looks like, we could draw this like this. See another one. This whole distance here is 2 nanometer. And this one term here is about 3.4 nanometer with 10.5 base pair. We call it BP. And this is called major growth. This is called a minor growth. We don't need to worry about that. How they connected with each other? A complement with T, G complement with C. This is hydrogen bonds. Okay, what are the other two bonds when you learn your chemistry? Ionic bonds and, for example, this is ionic bonds, and covalent bonds. For example, is that right? That's hydrogen. Hydrogen bonds is a weak bond. So that's why they can break. And you need to know they're running through 5 prime to 3 prime, 3 prime to 5 prime is opposite direction. Okay? Now once they have this one connected together, how they do it? Okay, I have a carbon right here. This is a base. Let's say this is H, this is H, this is H. Okay, H, this is O. Okay, this is CH2. You go here O, you go here P. Okay, you go here. This is P. Do you have another one like here? This is another base. H, 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 O, H. So, how they do? 5 prime, 3 prime, 5 prime, 3 prime. They go this direction. And we always say this single one right here with 5 carbon sugar with base and with phosphate, this single thing, we call it a nuclear side. Is that right? We call this the nuclear side with this guy. And then, once we with a phosphate, this whole thing, we call it a nucleic tide. And then we go long and long and long and long, going through polymerization, like this, we call it nuclear gases. This is what I explain you to in the DNA structure. Nuclear side, deoxynucleoside, the phosphate become a nucleotide and going through polymerization is nucleic acids. And when you see here, this structure, middle right here, this is called diphosphester bonds. Okay, so this is the structure for DNA. It's not difficult. It's just that you have to understand it, and you can see it's right there. The structure, what is there? We have a base, we have an amino acid group, we have a base, we have a 5-carbon deoxyribose, then we have the phosphates. This is the basic structure. They complement with A and T, G, and C. And then this is a picture which is, you see the phosphodiester bonds. And they always running opposite direction. The hydrogen bonds connected with A and T and G and C. Now, by the way, A and T, there's 2 hydrogen bonds, and G and C has 3 hydrogen bonds. So, when you design the primer of the PCR, you need to thinking about the amount of the GC components because they have more hydrogen bonds. Okay? So that's a very basic story about the DNA. And this is also the DNA structure in another way which is explained to you how good it is. If you don't understand it, This is the DNA structure. So we're going to talk about DNA replication then. Okay, the DNA replication, we talk about history, 1953. They find the DNA structure, double helix. So we're going to talk this out. We're going to talk about DNA replication. So we talk about these things, we move these out. Maybe left this guy. Okay, so DNA replication. We have double helix like this. They are running opposite direction. 5 prime to 3 prime, and 3 prime to 5 prime. And we already know the DNA replication we call it semi-conservative. What do you mean semi-conservative? They always break down the double bonds and then, based on gene complement policy, to biosynthesis their new daughter bands. In the history, the semi-conservative DNA replication theory is verified by 2 very important scientists. Yes, Mendelssohn and Starr research. Matt Mendelssohn and Frank Starr. These 2 scientists at the time is very young. It's about 1955. They both are graduate PhD students at Caltech University. So Caltech University is a very famous, important private institution. They generate all the young prodigies, or we say, the talented people. So you see the young Sheldon, you see the Big Bang theory, what he works from is Caltech University. So that's why I let you know some of the background. So Matt Mendelssohn and Frank Starr, what they did. You have a DNA from a bacteria, let's say from E. coli. Okay, I'm going to label them using an isotope. Is N, this is originally is N14. Is that right? Originally, the chemical molecular weight of nitrogen is N14. Is N14. So what we do, they grow it in a bacterial media with N15. This is another isotope. But it's not a radiation. It is only the molecular weight is heavy. So what happened? These 2 double bonds will be separate. So what happened is this N15 will be go there. This N15 will be go there. So the first generation, one is N14, another one is N15. One N14, another one is N15. Okay, how about the next generation, what it looks like? So next generation you will see, it looks like this. But more and more you will see is these double bonds showed out. And more comes out. So what you can see is, with more generation comes out, the dominant components will be N15. Is that right? If I do more and more, the dominant components will be the N15. So how do you do? They do that is in a centrifuge. They have centrifuge. high-speed centrifuge. And they messed it up with Sicilian chloride. And what they find that it's right here, this is about 75% is, the precipitation is N15, and on the top is less than 25% is N14. This is well explained, the semi-conservative replication. Because with more and more generation, due to replication, the N15 will be the dominant component. So finally, it's going to be more than 90%. Okay? So that's a very important Matt Medelson and Frank Starr research. Using the high-speed centrifuge to verify the semi-conservative replication. So what is DNA replication really looks like? Here we talk about the DNA replication. We'll be using E. coli as a model. In your class, you may using fungi, but we only using E. coli. So, E. coli, you need to know, it is a prokaryotes. It is circular, and everything happened is a replication fork. So this is what happens in there. Okay. So at the beginning, you have two double bonds. The two double bonds, 3' to 5', 5' to 3'. They are running opposite direction. Everything happened in the beginning is at replication fork. At the beginning, they need 3 major DNA protein, which is A, B, C. Then A, we call it the DNA, is initiator. So they initiate the replication. Then a B, DNA B protein, is a helicase. What means a helicase? Which means we need to separate them. Okay, separate the double bonds. Then a C protein is a helper. Or we say it's a holder. It is then a B protein, which is a helicase is a holder. You hold on that. So they separated. Because DNA is a highly twisted double helix, anti-parallel, by the way. So they need to make sure they are separate. We need these type of the proteins there. This is called SSB, single binding protein. We need those single strand binding protein. We need those there to make sure they are separate. Okay, now they started to do replication. Let's just give you some example. Okay, I like to write OH, A, P, T, P, C, P, G, P. Because this one is 3' to 5'. When DNA start to do the replication, they need a primerase. So they need an RNA primerase. That's all they needed. So, when you have a 3' to 5', they can, because their replication is always 5' to 3'. This is, you know about that. So they start to do the replication. So what happened is P, A, P, T, P, A, P, G, P, C, and this is OH. And of course, you have lots of like APP, like TPP, like CPP. These are free available gene base is there. Okay, they can continue coming based on gene complement policy. So the top one, they are from 5' to 3'. With this direction, They can do it naturally. They rely on enzyme, which is DNA polymerase 3. Now, by the way, who created the DNA polymerase is a great American chemist, Arthur Kronenberg. He won the Nobel Prize in 1970s. And his son, Roger Kronenberg, is also win the Nobel Prize later in 1994, and he founded the RNA polymerase. So we're going to talk about that later. So this is the polymerization process, which is rely on DNA polymerase 3, because luckily we have this enzyme, which is called the DNA polymerase 3. So here is the thing. This is a leading band, we know that. From 5' to 3', we can go ahead to do. But why they cannot go the opposite direction? You have a 5' to 3'. They cannot go this way to naturally happen. They need to still rely on 5' to 3'. Is that right? They still have to do this. They have to do this. And once they started, they need those small segments. They need an RNA polymerase, and then they need to have these small piece segments. And these small segments called Okazaki segment. Now, why they need to do that? This is a question lots of people doesn't understand. There are two reasons. One of the reasons, lots of people will say the structure. So I left it here. From 5' to 3', you have free available hydroxy bonds there. You can go ahead to do connection. You go opposite direction, that's not available. So the first reason is no free available hydroxy bond. The second reason is the energy reason. Okay, once you have these connected, every time is phosphate coming, is that right? Phosphate is an energy currency, like you're going here, let's say ATGC. This is from 5' to 3'. So it's naturally, you come in, you carry 3-phosphate. Looks like you are pay the money, because they're going to hydrolyze use ATP, okay? You pay the money, you're going to go to the gate. Let's say this is the gate. Okay, if I do opposite direction, what I have to do? You need to break down. You need to insert. This is for energy policy. It's not going to work. Because there's no spontaneous reaction going to happen. Think about this way. This is the gate. Everybody goes there. Everybody goes there. Okay, this is the line. If you want to go the opposite direction, what do? You have to break the line. Does anybody want to do it? No. Let's say this is the gate, and they go to see a football at the stadium. You're going to be all in the queue like that. You don't want to break it, other people insert. Because other people insert, everybody have to back. That takes energy. It's the same thing. So the energy is not workable. You do the opposite direction. So, for this lagging band, they don't have any choice. They need the RNA polymerase to have a primer. Because RNA primers, they don't have this restriction to form all these small segments, which is called Okazaki segments. But once they have Okazaki segments, what you have to do? These RNA primer have to be cut. This rely on DNA polymerase 1. Now, by the way, DNA polymerase have a lot of that. They have 1, 2, 3, 4, and 5. We don't mention DNA polymerase 2. This is different molecular weight. This is used for SOS response of the mutations. So these things using DNA polymers one have to cut. But once you cut it, there is a space you have to connect it. This relies on DNA ligase. You have to connect it. Okay? It becomes long and long, long and long. So this is a procedure how we do. Okay, looks like we're done, but not done yet. We want to talk about something else. Okay, once the DNA replication finished, they just finished, there remaining two big issues. The first issue is topological issue. What is the topological issue? DNA is highly twisted double bonds, like this. You separate them to do the DNA replication. There is always a tendency they have to be twisted back. So there is a topological issue. We have to lose the tense between that. Luckily, we had an enzyme. The enzyme called topoisomerase. They could change positive supercoiled DNA become negative supercoiled. And this topoisomerase specifically in E. coli, this is called DNA gyrase. Very specific, because we talk about E. coli all the time. So this is the first issue, is topological issue. The second issue is fidelity issue. So we talk about the replication. Ideally, the mother bands and the daughter bands should be exactly the same following gene complementary policy. But unfortunately, it is not. So let's say if we don't do anything, a single cell division will happen. The mistake is 10 to the 3. 10 to the power of negative 3. And this is very high. This is one cell among 1,000 cells will have a mistake. So the fidelity issue, we have to solve the problem. And luckily, we have some tools. The first thing what we could do, we rely on DNA polymerase 3. Because DNA polymerase 3 have endonuclease function. Which means if you have ATGC, TACG, if I have TACC, I could find it. And I can cut it and then replace with G. So that's called endonuclease. So DNA polymerase 3, the function, is like proofreading. This is like you write a thesis. After you're done, before submit, you need to make sure all the spelling is correct, all the grammar correct. This is called proofreading. So rely on DNA polymerase 3, and this could be decrease the mistake rate around 10 to the minus 5 to 10 to the minus 6. But is this enough? Of course not. Because any of the mutation happens in the human being will cause the cancer. So for example, the human colon cancer is because of DNA replication, the errors has not been solved, which means the fidelity issue is there. So the last one what we could do is we could add a methyl group there. So ATGC, you become the TTCG, for example. You see here, we could add a methyl group there. Then we fix it. We cut it, then we fix it. So that's called methylation, the last step. And the last step will break down the mistake around 10 to the power of 8 to 10 to the power of minus 9. That is usually is one error among 100 million to 1,000 million cell divisions. If you were using bacterial cell as a unit, this will be dramatically solve the fidelity issue. Okay? So, this is the whole thing. We talk about the DNA replication. You can see the slides. This is one I really like, which is explains to you the whole picture of the DNA replication and the enzyme. This is talk about the procedure. And this is all the enzyme function, the protein and the function. This is well explains to you the 5' to 3'. This is from one point of view talk about the structure. Because if you go opposite directions, there is no free available 3' hydroxy base. So you cannot go the opposite direction. But I also talk about from the energy standpoint, from the other direction, it's not going to work. And this is giving you something, talk about DNA polymerase. It is also a hollow end enzyme. Then we talk about the helical single-strand binding protein, topoisomerase, and this is also a very nice picture. On the right side, you should highlight this one. This is well explained to you. The leading band, the lagging band, Okazaki segments, and how they happen. And this is the synthesis, the process, and this is we talk about the ligase cuts the Okazaki segments, the proofreading, which is a fidelity issue. One of that we could be using DNA polymerase 3. And finally, the termination. Well, once you have a termination, you have a signal like a TER, then the stop to do the replication, and topoisomerase will be break down there. So the release the tension from positive to negative supercoiled. Okay, so that's all we have for the DNA replication. We're going to talk about transcription translation on Thursday.